So this is our training rig. You won't find any training rig like this. You won't find anything like this on site, but you will find all four main components, which is the compressor, the condenser, the TEV or metering device or TXV, and the evaporator. There are four main components, and then we're going to look at some line components on here as well. All systems have the same setup, from your smallest fridge to a giant chiller. They will all have those four main components. So let's take a look at these components. So first of all, here we have our compressor. Okay, this will take, we call this a little pot really in the trade. This will take low temperature, low pressure vapor, and it will convert it to a high pressure, high temperature vapor. Push all them molecules together, and it will eject them basically out of our discharge line. Okay, so we come out of our discharge line, we're looking for about 80 degrees usually on something like this, and we'll be de-superheating all the way around this system. So we come out of our discharge line here, and as we come down our discharge, as we come down, we carry on de-superheating, losing kilojoules per kilogram to the ambient air, and we come down and we come into here. This is our high side. This is a rotor lock, and we can attach gauges here. Here we have an isolation. Here we have a stem, I should say, and that could be a main leak point because it's got packing glands. So we could leak from there. So we have to be careful all the time to check this. This we can consider as a safety valve. We can remove that, and there's a stem on there, and we just use our service keys basically to open them up. So as we come through here, as we go up, we carry on down. Our discharge comes down here to the side, if you can see that. We come down here, and we come through, and we carry on with our discharge. We go round the back of the compressor. Here we have a little capacitor here in our electrics. We come through here, and then we come up, because vapor will always be at the top of your condenser. Okay, it's a high pressure, high temperature, superheated vapor. So as we come into here, this is the first, this is the, the second of our components, our main components here, and this is our condenser. We have air on to our condenser, and we have air off of our condenser. Okay, we'll flip this around because we like to keep our compressor cool. When we're talking about a fan assisted system, we want a 15 degree or 15 Kelvin, we should say, split, or TD, temperature difference. Okay, so if I had a ambient of 30 degrees and I had a temperature probe and I was holding it here and it was recording 30 degrees, I'd be looking for a temperature of 45 coming off of here. Yeah, 15 degrees, so we're looking at a 15 degree split there, okay? So we'll go through here, through our coils, as you can see here. These are leak points as well, of course. Anywhere there's a join there, and we go through, and this is no more than a heat exchanger. There's no reason to get concerned, it's just a heat exchanger. It gets rid of all that heat. Kilojoules per kilogram. Here on top, we can see our service information. So we've got unit 9, we're using a refrigerant 449A. We should have a charge of 3.5 kilograms. And there's the GWP for our 449, which is 1,397. And it's a safety group A1, which means it's non-flammable and non-toxic. Okay. So then we come through here. As we change states, as we're releasing all that energy, as we're getting rid of all of that energy, we're changing states from a vapor down to a liquid. Okay, so then we come out of here, and we're at the bottom now. We come out of that condenser, and we're coming out as a liquid. There you can see a little temperature probe there. If I can just show you that, you've got a little temperature probe, so we can take our liquid line subcooling temperature. And then we come along back here. Here's our liquid line here. And we come up our liquid line, and then we drop into our first of our line components, which is our liquid receiver. Okay, in our liquid receiver, we have, because it's a bigger vessel, it's going into a bigger volume area, we have a two-state mix. So we have vapor and we have liquid. We have liquid sitting at the bottom there, and we have vapor. And how we use this, the reason we use this is for this, we use this in varying load conditions. So we use it in high load and low load conditions. In low load conditions, it can store refrigerant, and in high load, obviously it'll be a lot lower. It's basically a buffer vessel. Any sealed system, whether it be hot or cold, will always have a buffer tank, a header tank, and we have that. We call that a liquid receiver. We'll also use this for pump down scenarios. So we can attach gauges to here, our liquid line, which we can also call our high side if you like. We can attach our high side gauge to that. We can attach here, and we can use this for a pump down. We can do pump down, and which we'll be showing you as the course progresses. So we come out of our liquid line. We have a little short stem here going in, and a longer stem coming up onto this line. We come into our liquid line, we come down, and we hit the second of our line components. This is our filter dryer. It does exactly what it says on the tin. It filters and it dries. It keeps all the non-combustibles. It should trap any little particles, water moisture, I should say, little drops of water moisture. That should trap that. That should trap all of that. If I was to put a temperature probe here, I would want the same TD. Basically, I would want the same split. I would want the same temperature. If I got a different temperature going across that, I would be concerned. I would think that could have a blockage on there, and I'd want to change that. Whenever we break into a system, we call it breaking into a system, out on site, we would want to change this really every time. So that's our second, that's our filter dryer. As we come down our liquid line, we are our third line component. Here's our solenoid. Okay, we can remove this cap. If I can just get this here. We can just remove that. And I could place a magnet on there to lift up that valve. All that is an isolation valve. That's all it is. It's simply an isolation valve. We have, this could be a leak point round here, because once again we have some packing, okay, going on there. These mechanical joints, they could be a leak issue. Okay, anywhere like that could be a leak issue. But we use this solenoid to isolate, to do a pump down, to perform a pump down. Okay, so then we come through, I'll place that back on shortly. We come through our liquid line, and we hit this, we hit our sight glass. Okay, this is our sight glass. As you can see there, there's a little symbol, and it says wet and dry. That will change colour, and that just indicates if we have any moisture in there. Now what we do, what as engineers we say, is we look to charge to a full sight glass. We shouldn't, it's one of those things in the profession we shouldn't do, but we do. You'll often hear an engineer say you should charge to a full sight glass. What they're actually saying is they want 100% pure saturated liquid at this point, because we want 100% liquid going into this. This is our metering device. In this case, this is a TXV, okay? We know it's a TXV because here we have an equalisation line, and TEVs will not have this line. It's a sort of buffer between the two, and it just keeps it regulated nicely. So what does our TXV do? It drops our pressure and temperature dramatically. We get no change in entropy, it just drops that pressure and temperature. Here's our capillary coming off of there, and there's this, there is going onto our valve. Inside there, there's a little diaphragm that it pushes down on. And then we come down, if we look at our capillary down here, we just go on here to this point here, and this is our bulb. Okay, and we've got that sealed off to the ambient. We don't want no ambient air going onto there. We come through there, we go into our evaporator. And our evaporator, what does that do? That takes in the air. It takes in those kilojoules per kilogram heat energy. Heat energy. It takes in that kilojoules per kilogram, or enthalpy we can call it if we want. And it will come in here and we'll have another heat transfer. And this is where we get our cooling from. Okay, our cooling will come out of here. So we go through our evaporator, back along and up here. This is called our suction line. We can tell it's our suction line because it's got arm flex lagging on there. And that's for the condensation. We come to here, this is another isolation point, a ball valve. This is no different to any ball valve you'll find under your toilets, under your sinks. It's simply a ball that rotates to cut off the flow. We then come along, this is our test piece that we use at times. And then we come through here and we have our Schrader point. Now on our Schrader point, we can attach a torque gauge. We can attach a torque gauge to here, it's a little digital instrument, and we can record when we're pulling a vac. We need to pull a vac on here, and we'd look to go down to about 2 torr or 2,000 microns. Here's another isolation point, just put that on there. As you can see there on the top of that cap, we can just tighten that valve up. That valve there, as you can see, if you can see in there, it's no different. It's a depressed. You can just depress that. It's no different to what you find on a car tyre or your bike tyre. And on top of there, we can see a little adjustment point where we can tighten that up or change it, or replace it. We can replace those if we need to. So then we come through our suction line, through here, back into another rotor lock. This is our low side rotor lock. Okay, this has our low side valve. And then we come through our suction, lower temperature, we've dropped, we've de-superheated all the way around, and then we come back into our compressor, and that just continues. Unlike a car, we don't lose the energy, we just keep on transferring it.